All right, hello everyone. Today is June 6th. We're going to go over chapter 5 today, and we'll see if we have time to go into the homework. If we do, we'll go into it. So we'll go ahead and get started. This is about isomers and stereoisomers and enantiomers and enantiomeric excess. There's a little bit of rotating light. So does anyone have any questions for me before we get started? All right, so I'm going to go ahead and share my screen. So I know we went into it a little bit last week, but let's go into it a little bit again. It's not a bad idea to review. Get my pen. So isomers are different compounds that have the same formula. And we have two different types of isomers. We can have constitual isomers. They're going to have a different, same molecular formula, but different constitution. So the order of connectivity is different. That's the big deal right here. And stereoisomers, they're going to have some type of mirror plane is what we're going to see. Same molecular formula and constitution, but different spatial arrangement of atoms. So here we have the cis and trans designations. Later on in the book, in this chapter, we're going to see that this is going to be the Z and this is going to be the E. But here we learned up to now that the cis is on the same side, the trans is on opposite sides. So groups on the same pi bond, we have cis and we have trans. Although the two molecules below have the same connectivity, they are not identical, so they are stereoisomers. And stereoisomers have the same molecular formula and constitution, but different spatial arrangement of atoms, which is different than your constitutional isomers. And we did go over this problem last week. So I'll just give you I think I'm on though. Okay, I was just making sure I'm showing the correct screen. So these ones are gonna be identical. This one's identical too. If you just flip this like this, you're gonna get the same thing. These are stereoisomers. So remember, stereoisomers are the same molecular formula, but different spatial arrangement. I'm looking at the middle compounds. They're going to be stereoisomers. And this one, are going to be constitutional isomers. They have the same molecular formula, but different order of connectivity. If you count all this, how many carbons, we did this last week, but you count 1, 2, 3, 4. They both have 4 carbons. I should have started that on the other side. And you can count, they're going to have the same number of oxygens and same number of hydrogens. So I'll let you look at that for a little bit. You should be able to, identify, if it's identical, or they're stereoisomers, or they're constitutional isomers. Identical, they're just the same molecule. We just flipped it a different way. I'll check the chat. All right, I don't see any questions. They put the answers too. Other seeing, are these either cis or trans? Now this one is going to be cis, trans. It's going to be trans. If you think about this as a hydrogen here, there's a hydrogen here. So we're looking at this group right here. It kind of goes opposite. And I can draw that. If you draw it like this, it probably looks a lot better. You can see that trans relationship here. I'm going to say this one's neither. Yes. If it was something like this, it'd definitely be trans, because then we're looking at this right here. This is a longer group. These are equal here. So you could either go like this, or you could go like this and be the same. These are not the correct answers right here. That was for the other problem. So cis-trans isomerism is only one type. There are other important stereoisomeric relationships. We have chiral centers, and we're going to talk about being an R or S designator. So chiral center is asymmetric, which means it is not the same as its mirror image. But it's non-superimposable on its mirror image. So basically, we're going to have one hand in your left hand, your right and your left hand, and you're going to have mirror images, but you're not going to be able to put your right hand over your left hand and get the same thing. It says you can test whether two objects are identical by seeing if they are superimposable. So I'll leave that there because there's some important definitions on this slide. All right. So chirality is important in molecules because two chiral molecules are mirror images. The reasons why they're important is because of the pharmacological difference. something might be active in the S form or something might be active in the R form. Visualizing mirror images. So they're talking about visualizing. We're going to do that on the next slide. So that's why it's important to have handheld models, because you may need it to visualize. So, those that have handheld models, I'm just going to leave some of these slides open. That way you can practice. So if you have a handheld model, usually the red one's the hydrogen, and it could be different. So in this case, it's an oxygen. So let's just keep it that way. They're saying this is a carbon right here, representing this as a methyl group. Here there's a hydrogen, and here this ET, that's an ethyl group. So that'd be 2 carbons coming off right here. So you have one carbon, 2 carbons, that oxygen with an OH. So now if you rotate it this way right here, that ethyl group will be here, followed by the methyl group, followed by the hydrogen. But they have a mirror plane. So I'm going to give those who have the model set some time to make these models. That way you can see for yourself, that it does have a mirror plane and it's non-superimposable. That means if you put your hands, if you put it right over top of each other, you should get the same thing. So if I flip this around like this, 120 degrees, if I turn it around, then this hydrogen will be here as it is. And let's just draw it right here, actually. So that OH is not going to do it because we're turning it around the OH. So nothing's going to happen there. This hydrogen is going to be here. Now, coming out right here, this will be the methyl group. And coming in will be the ethyl group. So take your models and see if you can, see if you get the same thing. Does anyone need more time on their models? All right. So right here, it says, they want you to practice finding stereoisomers on the stereo center. You have to find the one with the carbon that has 4 different groups attached to it. And they say that right here, 4 different groups. So let's just look at this one. What they're not showing is this hydrogen coming out, or I guess going into the screen. So this chlorine right here, you have 1 different group, 2 different groups, 3 different groups. So this would go this way. And since it's going clockwise, it's called the R. Here we have this hydrogen right here. We have 1 different group, 2. This would be the 3rd. Kind of going like this. This would be an S. 1, 2, 3. This would be an R center. And you determine R or S, you look at the bigger ones. So here we have a carbon and a double bond. So a carbon with a double bond has more weight than a carbon with a single bond. So that's why I designate this a 2 here. Likewise, over here, we have more stuff coming off this one with the 2. See that? We have 1, 2, 3. We have 1, 2 carbons here. So that has more carbons, has more weight. So that's why I'm giving it a 2 designator. So why don't you try to identify the ones that have chiral centers and the ones that have no chiral centers here. And you can go ahead and look on the next slide. But before you look on the next slide, really try to see, if you can get them down. And if you did identify the 2, one has chiral centers, tell me which one does, or where they're at. So we'll go to the next slide. So the top left one has no chiral centers. You may have thought maybe it was right here, but if you go down this plane right here, we go down this one right here, everything is equal. Equal here, equal there. That means we have the same stuff coming off. You're going to have, here's a carbon, that has 2 hydrogens. Here's a carbon with 2 hydrogens. There's nothing different here. There's nothing different here. There's nothing different here. So if we go down here, we have all the same stuff. That's why there's no chiral centers. Here, let's look at the one on the top right then. Here we have 2 chiral centers. You have, let's just, for instance, we looked at this one. Now, if we go down here, we see we have an oxygen coming off right here. We have carbons first. But we have CH2, but then here's an oxygen and here's a hydrogen. So we have something different. So we have a chiral center right here. Now let's go to the bottom right. We have a chiral center here and a chiral center here. And why is that? Well, we go right here, we have a carbon, we go right here, we have a carbon, we go right here, we have a carbon. Now we have a CH3, which is different. We have a CH2. With another carbon coming here, and here we have a CH, so this is already different just by looking at these ones. Here, this says it has 2 chiral centers. Let's just look at the middle. Actually, let's look at this side right here. We have carbon, just CH3, CH3. So, that's not going to be a chiral center then, is it? Here's your chiral centers right here. Does everyone see why this is not a chiral center? It's because all four substituents coming off have to be different. But let's just look at that. We know that I showed you where the two chiral centers are. So let's see why. Okay, so we have a carbon here. We have carbon here, but this is CH3, with CH2, and with CH. And here is this hydrogen, so everything's different. So that's why you have a chiral center right there. Now, if we look here, then we have this hydrogen coming off, which it doesn't show, but it's there. And we have this carbon, we have a CH3. Okay, so these are the same. Now we have a CH3 here, which is a CH3 here, which is CH3 here. But now I'm just looking down this path. Now this path is a little different now, isn't it? We have a CH2, which is different than this side over here. So that's why there's a chiral center right here. So it may not be DR, so we're going to put that as a chiral center. This is not the chiral center there. That's why I'm putting an X through it. So we identified the chiral centers. And I'll leave, you to do this at home, quickly. I can see a chiral center here, 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 here. No, not there, because this is the same stuff. See, does everyone see why this is not a chiral center? Because this is a CH3, this is CH3. And here's a hydrogen, so these are the same thing, right? These are identical. So it's not going to be a chiral center there. All right, I might have identified them all for you there. So it says some stereoisomers can also be classified as enantiomers. Enantiomers are two molecules that are mirror images but are not superimposable. And we saw an example where you practice with your model set. It says this is a chiral center. The mirror image will be its enantiomer, and on the next slide it shows you enantiomer. So we'll just go there, and that's the mirror image. So what that means is, and I'll draw the hydrogens here. That if we take this molecule, this is where it'd be nice to have your model set, and you try to superimpose this on this one, you're going to end up with the chlorine here and the hydrogen here. That's why it's non-superimposable, because you're going to have the chlorine here and the hydrogen here if you try to put them on top of each other. So I'm going to leave that so you can, try to manipulate that 3D image in your mind. Or if you have a model set, then take out your model set and try to create this. The best advice I have is just study a little bit, every day. That will really help out, with what you need to do. Right here on the next slide, so we've seen that these are enantiomers, but you can go ahead and practice, seeing why these are enantiomers. Here we have it going back. Here we have this coming out. I'll show you the ones that to look for. I won't. Right here, you're looking at this chlorine. You're looking at this OH group. Just take a little bit and look at that. So hopefully that's all making sense to everyone. It says enantiomers are different compounds, so they can't have identical names. That's why in the beginning I started talking about this R and S designator. If a compound has the R configuration, then the enantiomer will have the S configuration. So its enantiomer means the other compound. So if this one has the R, this one will be the S. So we have 1, 2, 3, with 1, 2, 3, goes clockwise. This one goes clockwise too, but since the hydrogen's coming out, you flip the answer. So R then becomes S, and this is an S right here. You flip it when the hydrogen is pointing out, and you're gonna flip your answer from R to S. And the reason why you do that is, imagine that you rotated this 180 degrees. So let's just try to rotate that 180 degrees. So let me think about that. And we now put the chlorine here, the hydrogen here. So then it goes this way, doesn't it? That's why when the hydrogen's coming out, you flip the answer, because when you put the chlorine in front, you get the 1, 2, no, 1, 2, and 3 this way. So it's counterclockwise. So RRS are assigned to a chiral center using a stepwise procedure. Using atomic numbers, prioritize the 4 groups, and I kind of showed you that already. Arrange the molecule in space so the lowest priority group faces away from you, and that's why I always put the hydrogen away from me. It says a handheld model can be very helpful, a very helpful visual aid for this process, and that's really true. That's why you want to have that handheld model. That way you can see visually why this is true. Let me get my pen here. And you don't have to redraw it like that. You could have just said, oh, here's your 1, here's your 2, here's your 3. No, you go this way then. No, sorry about that. You go this way. It's R, but since the lowest priority is sticking out, you have to flip that to the S. So you don't have to redraw it like this. I'm just showing you, why that is the case. And the priority is assigned by, which one is the biggest. So chlorine is bigger than oxygen. You look that up on the periodic table. All right. So hopefully this is making a little more sense. So they're just going through the process showing you why it's the S designator. And, I think I did a pretty good explanation right here. So does anyone have any questions on why this is S? All right. It says when the groups are attached to a chiral center or similar, it can be tricky to prioritize them. So you have to analyze atomic numbers one layer of atoms at a time. So that means you just go to the next one out. Here they say when we have a tie because there's 2 CH2 groups here, and you keep going out. Here's a CH2. At the next one out, you have, a CH group attached to 2 different things. So that's a tiebreaker. So in this case, who's going to win? Even though there's more stuff and it's more molecular weight, the tiebreaker is going to go here because there's 2 carbons right here, right? You have a CHH, CHH, and let's just go with how they're doing it. Here we have a CHH here. Just looking at this one. Here I have a C, H. I also have actually 2 carbons here. You have 2 carbons right here, which are going to beat, anything over here. So they do it a little different than how I would set it up. Here we have a CH2 with another carbon coming off. Here we have, it's carbon. We have another carbon here, another carbon here, and a hydrogen. So we have more carbons coming off than this one right here. This one has 2 carbons, this one has 1 carbon, so this is going to go over here. So the tiebreaker is over here. So we have 1, 2, 3. And so this would go this way. it would be S, but we have to flip it since the lowest priority is out in front, so this is an R. And they're just going through, layers of tiebreakers here. Here they're saying if you have a tie right here, well, what's going to win? The priority is based on the first point difference. So, we have an oxygen versus a carbon. You have an oxygen here. You have a carbon, so the oxygen's gonna win. So you have this is gonna be a bigger priority on this side than so bigger priority. So we go this way. So that would be R, because remember, if it goes that way, it's S, but we have to flip it because the hydrogen's in front. So you flip S to R. So that's why you're getting an R right there. Okay. So they're saying this double bond counts as 2 single bonds here. So if we're going to give priority, we look down the path. Everyone has a carbon, right? So the first one's not going to do anything. Now we look down this one. This is going to be the winner right here because it has two, oxygen's bigger than carbon. So it has two single or a double bond, and it says you're going to count it twice. So this is your bigger one. So here's your one. This is going to be your lowest priority. This will be 4. 2. Actually, I should put like this. So it goes on like that. That'd be R, but since the lowest priority is a 4, it's sticking out front, it turns into S. I'm taking my time through this because I know this can be difficult for some students to visualize, so I want to take my time. This is just talking about using handheld models. So, and they're talking about helpful tricks. So if you have a handheld model, this is when you would get it out. I'm not going to go over too much of this because I don't have a handheld model, but if you do, follow these helpful tips and tricks. And right here, they're talking about rules to help for the assigning. We kind of done that already with our example, so I'm gonna go past this a little bit. So here it says assign the configuration of the chiral center in the following compound. So first you have to find the chiral center. So I'll give you a minute to find the chiral center and to identify whether that chiral center is R or S. All right. So I'll show you where the chiral center is. It's right here. So if you got that, that's good. So once you now know you know where the chiral center is, now try to determine whether it's R or S. So you're gonna be, what they're not showing you here is a hydrogen. So we'll draw that in for you. So you're gonna be looking down the centers, right? You're gonna say, oh, I'm gonna look down this one, look down this one, I'm gonna look down this side. And I'm gonna get rid of that because I want you to see the dash. The dash is right there. So that means you gotta get out your periodic table. So your large priority is going to be this one, followed by this one, because nitrogen is bigger than carbon, followed by this one. Even though there's more stuff coming off and this is a higher molecular weight, we're looking at, what's the next one down. So this would be nitrogen versus carbon. Actually, I think I have that wrong. Good thing I looked at it myself. So you have a nitrogen. This is actually going to be your biggest priority, because think about this. Nitrogen is bigger than carbon. So that's why we're going to put a 1 here, followed by 2 here, followed by 3. So it's going to go this way. And since that hydrogen is sticking out, it's sticking out. We're going to have to flip our answer. So we went clockwise. So we're going to R, and then we're going to convert that to S. So this is your S right here. So when I drew it out myself, I caught myself with a mistake. I was initially thinking that this is going to be 1 because of the oxygens, but then I thought, well, it doesn't matter. What matters is what's next, and nitrogen is bigger than carbon. So therefore, we're going to give that the higher designator. Any questions on why we assign that S? All right. All right, so they give you the answers here. So, how do you even get 2? Okay, you get 1, 2, 1, 2. Here we go. 1, 2, 3, 4, 5. So you have 2 butanol. So that means there's a hydrogen coming out here, right? So here's your larger priority. This is oxygen. So you have 1, 2, 3. That's how you get R. We have 1, 2, 3. Remember, we're not showing the hydrogen sticking out, but it is sticking out, isn't it? If this is sticking back, you have to have the hydrogen sticking out. So 1, 2, 3. This is gonna be your S, because it goes R, but we're gonna flip it to S because that hydrogen's sticking out. Here we have 2 chiral centers here on the bottom one. We have 1, 2, 3. Here's your R. I'm going to erase this to make it easier. Here we have a carbon. Here we have a carbon. Here we have a carbon. So I can't really tell what's the bigger one by just going down the first time. But if I look, starting going here, coming off here, coming off here, I'm going to make this a dash. Actually, I'm going to do the dash for the second one. So let me do this. 1. So they're all equal here. Now I'm going to come use my dashes. So what's the bigger priority? Well, oxygen is the bigger priority. So we have 1, 2, 3. And remember, we have the hydrogen sticking out. So that'd be S. Right. So here we have R and here we have S. Says because the structure of the nature is only different in the same way, your right hand differs from your left. They have the same physical properties. So we can see that they have the same physical properties, but pharmacologically they're different. And they rotate light differently too. They'll either rotate light to the right, and just because something is S doesn't mean it's going to rotate, or R doesn't mean it's going to rotate light to the right. It could rotate light to the left. Here we have your hydrogen coming there. And so we know the hydrogen's going back. So let me see about this. Does everyone see how I got R and S now? If you don't, this is your time to speak up too. All right, so I'll assume everyone knows how to do that. Now they talk about this thing called plane polarized light. So polarized light, I taught the microscopy course for a couple of years. That's basically how to use a microscope. So in microscopy, we teach that we have something called polarized light. What polarized light means, if you imagine a flashlight or a beam of light, you have light going in all different types of directions, right? Here they're only showing it going in, they're showing an electrical wave with a magnetic wave. But if we look at just polarized light, we're going to have light going in all different directions. And that's how I want to try to imagine it with this right here. Now, if I look at plane polarized light, we're going to take that polarized light what we're going to do is we're going to apply a filter to it. And let's just say, this filter is only going to let light pass that goes in this direction. So this light might go through, this one right here. And when it hits a sample, now that sample is going to rotate that light in a specific direction then. So that's what we mean by plane polarized light. So this is polarized light. This would be plane polarized light because we're filtering it through a plane, and it's a plane polarized light. And they do a good example on this slide right here. So I wanted to try to show it to you. But you take that, this could be any light source. And you have this filter. And the light passes through that filter, and that's what we're seeing right here. And you can get some really good optics when you look at plane polarized light. That's why they do that for. Some in some instances, when you're looking at microscopy, when you look at plane polarized light, that substance might turn a color, and that's due to this filter. Now there's something called cross polars where then you'd rotate the light again, but that's going more in depth in theory in microscopy. So I'll leave that to those that are going to be taking that class in the fall. So when plane polarized light is passed through a sample of a chiral compound, the plane that light travels on will rotate. So compounds that can rotate plane polarized light are optically active. only chiral compounds are octavely active. So that means if it was an enantiomer, it wouldn't be octavely active. It would just be dark. And you may not see it because you don't, sometimes we talk about, there's other types of light such as, there's UV light, which, you're not going to be able to see, right? The only type of light you're going to be able to see is colored light, and it goes from like 400 nanometers up to like 780 nanometers. So visible light is what I should have called it. This polarimeter tube, it has a certain length, So the plane of polarization of the emerging light is not the same as that of the entering polarized light. So you have your light source, you have your polarizer, which is fixed, polarizer tube, and you're going to have your sample in here, and it's going to rotate light either to the right or to the left. So if you have your sample in here, and somehow the sample is going to rotate light to the right or to the left. Now, if it doesn't rotate light, that means it's going to be a 50-50 mixture of the R and S. Because only if it's a 50-50 mixture of R and S, it's not going to rotate light. But if we have 60 R, 40 S, then we're going to rotate light more to the R. And it may not just rotate light to the left, it could rotate it to the right. So I just want you to know that. So you actually have to go and measure this to get, to see whether it rotates light to the right or to the left. I think this is a good time to take a break. So let's come back at 11:06 and enjoy your break. Welcome back. I hope everyone had a great break. So we're going to get back to the slide. Let me see. We are recording, so good. So we left off on this slide right here. If you were listening asynchronously, you could just paused and, took your small little break. Here we looked at a polarimeter tube. Basically, you have that polarizer, and this is made out of a special material, but this is beyond this class, what type of materials these things are made out of. So just note that, you're going to rotate light either to the right or to the left. So enantiomers will rotate the plane of light to equal degrees, but in opposite directions. The degree to which light is rotated depends on the sample concentration of the path light, so it depends on concentration and path length. Standard optical rotation measurements are taken with 1 gram of a compound dissolved in 1 mil and with a path length of 1 decimeter for the light. So if you think about that, 1 meter, let me write that better. 1 meter equals 100 centimeters. So 1 decimeter would be 10 centimeters. So 1 decimeter equals 10 centimeters. It says temperature and the wavelength of light can also affect rotation and must be reported with measurements that are taken. So temperature has an effect and the wavelength of light that is used for rotation. So you have to report both. So factors that govern the angle of rotation. So as the concentration of a chiral compound increases, so does the angle of rotation. As the length of the sample tube increases, so does the angle of rotation. So these are, parameters that will, we already talked about 1 decimeter equals 1/10 of a meter, and 1/10 of a meter equals 10 centimeters. The specific rotation is a constant that is unique for a given chiral compound. You don't have to memorize these things. You'll see that you're only going to be required to do some basic calculations. It says enantiomers, this is important here. Enantiomers have equal but opposite specific rotation. So if one has, let's just say -50, the other one will be +50. So that's what they mean by that. given that everything is equal, so that it has to have equal concentrations at the same temperature. So if everything is equal, now if you have a different concentration, you'll have a little bit different number then. You will have a different number. So a racemic mixture contains equal amounts of the positive and negative enantiomers, and this is the rotation of light right here. So if it rotates light to the right, that's called dextrorotatory. If it rotates light to the left, it's called levorotatory. The light traveling through a racemic mixture encounters an equal number of molecules. Racemic mixture of enantiomers is optically inactive, so it's not going to rotate light to the left or right. So if a mixture of enantiomers is not racemic, remember I gave the example if it contains like 40 of this and 60% this, then it'll be octavely active. The excess percentage that favors one enantiomer is the enantiomeric excess, which is calculated using the following equation. So you have R and S for the chiral centers. Does everyone see why this is an R? Let's go through that. With this H here, this H coming out. So you have 1, 2, 3. Here we have R. And here we have 1, 2, 3. You know, I think it's R, but then we have to flip it to S because that hydrogen's coming out. So this is your S center. And remember, I told you just because it's R doesn't mean it's going to, you know, change light in the positive direction. Here we see that, you know, we're changing light to the left. So that's levorotatory. And they talk about that in the next slides, but, you know, we can put it right here. This is levo. This is dex. So you want to keep that in mind. And if we have, let's just say we have an S compound of something else, well, or an R compound of something else, it could rotate light, you know, in the in the dextrorotatory direction. So it depends. This is compound specific right here, whether it rotates light to the left or to the right. So the positive and negative sign refers to the direction that the plane of light is rotated. And that plane of light is this light right here. So you have your sample in here, and it's either going to rotate light to the right or it's going to rotate light to the left when it comes out of that sample. And this is what it's going to be seen right here to the observer. So the observer will be us, right? Or the instrument that is hooked up. I guess it'd be it would be us. I mean, the observer could be a computer too, is what I meant to say. And what's really important on the next slide, they said there is no correlation between R and S and positive. That means you can't say, oh, this is R, so it's going to be positive, and this is going to be S, so it's going to be negative. Oh, that's not true. Here, this said this compound, and try to find the enantiomer, the stereocenter. The stereocenter is right here. Let's be 1, 2, 3. So this would be S. Its optical rotation is levorotatory at 20 degrees, but if we heat this thing up, it becomes dextrorotatory at 100 degrees. So that's why it's important to note the temperature. So temperature is important. So the magnitude and direction of optical rotation cannot be predicted and has to be measured experimentally. So we can't just say, oh, I have this compound here. It has an S center and I'm going to predict that it's going to be, lever rotatory. Well, if we heat it up, it could be dextrorotatory or, whatever. So we have to take a measurement. A racemic mixture, a 50-50 mixture of two enantiomers, it's not going to rotate light. So it says, however, we can predict the rotation for a racemic mixture to be 0 degrees because it's going to cancel out. They're going to cancel out each other. So if we have negative, 51 and one enantiomer and we have positive 51, they're going to cancel each other out to 0. That's why we can predict it to be 0 for a racemic mixture. However, if one enantiomer is present in excess, so let's just say we have this one at, we have the R and the S. Your R is going to be at, let's just even put this at 10%. Your S is at 90%. Relative, then the mixture will have an optical rotation, but it will be less than the pure enantiomer. So it's going to rotate, but it's going to be less than if it was just 100% S then. And the rotation we're talking about is the rotation of light. So for unequal amounts of enantiomers, the enantiomer excess can be determined from the optical rotation. So it says, suppose a mixture of R and S, 2-bromobutane. So how do you get the 2? Let's go over that. Butane is 1, 2, 3, 4. That's how you get the butane. At the 2 position, we have a bromo group. Here, hydrogen, we're going to go 1, 2, 3. So this is R, and this will be S then. So suppose a mixture has a specific rotation of negative 4.6. This allows us to determine the percent enantiomeric excess. So EE is enantiomeric excess. You just put negative 4.6 divided by the negative 2.3 times 100, and you get 20% EE. And I'll let you go ahead and put that in your calculator, see if you get the same number. So this basically tells me 20% of the product is going to be the R. So 20% of my product is just going to be the R, while the other 80% is going to be a racemic mixture. So the other 80% would be a racemic mixture of R and S. So that means we would have, if you divide 80 divided by 2, which is 40, and you add the 40 plus 20, you'd have 60% of your material would be an R and 40% would be an S. All right. So enantiomers and diastereomers definitions, we took isomers and we said they're either constitutional isomers, different connectivity, other stereoisomers, same connectivity. Then, we looked at if they were enantiomers or diastereomers. Diastereomers are non-superimposable and no mirror image. And enantiomers are non-superimposable and they have a mirror image. So that's the difference between an enantiomer and a diastereomer. So enantiomers are stereoisomers that are mirror images, and diastereomers are stereoisomers that are not mirror images. And some examples of diastereomers would be the cis and the trans. And remember, enantiomers will have the same physical properties. So, same physical properties, except, when we're looking at, rotating light. But if we're looking at like melting point, it's going to have the same physical properties. Diastereomers, now, they're going to have different physical properties. Here we see we have cis-2-butene. We have trans-2-butenes. This is the trans, this is the same side. They're stereoisomers, but they're not mirror images of each other, because if you put this on this, you have the CH3 here. I'll put this in X. Now this X would be right here. So that's not a mirror image. Recall that enantiomers have identical physical properties, so diastereomers have different physical properties. Any questions on that? Wow. So stereoisomeric relationship. So consider cyclohexane. Cyclohexane is a six-membered ring. So we can see that six-membered ring right here. Here we have 1R, 2R, 3S. And let's just take a look at this and study this. Okay. It says there are 3 stereocenters here, and so there are 8 possible stereoisomers. Consider the relationship among them, enantiomers versus diastereomers. So some are going to be enantiomers, some are going to be diastereomers. If I look at here, this would be a hydrogen here. So we're going to go. Oh. So I'm just trying to, put them over. If I just flip it right here, I just turn them here, they're not gonna, but they are mirror images of each other. So these are mirror images. flip it this way, you're going to have the oxygen. So that's why having a model set would be really helpful in this case. The next slide is the same thing, the same images. It says, notice these 8 stereoisomers are composed of 4 pairs of enantiomers. That means if you flip this one right here, if you just turn it 180 degrees, the OH is going to, I'm going to draw this right here. That OH group now is going to be here. This methyl group is going to be here. And now since I flipped it, that chlorine group is going to be behind. So everyone just take a minute to see why that is. Here's your R. I just gotta get my periodic table out for a second. It's bigger, okay. This is R. This would be 1. And that thing coming out is hydrogen. Sorry about that. It would be 1, 2, 3, the S, but then we flip it so it's R. So the 1R is right here. Here's your 2, and here's your 3 position. But look at this right here. This should now be in the S. This is getting a little busy, so this should be S. That's all S's. Here, let's look at this one on the top left side. If this is 1, this would be 2, this would be 3, this would be R. This one would be 1. Chlorine is bigger than oxygen, so this would be R. This would be S. It's coming out here. So 1, 2, 3, it'd be R. All right, does anyone have any questions on how you get R's or S's here? Or why these are enantiomers? So next slide says the number of possible stereoisomers for a compound depends on the number of chiral centers. So you have to first identify the number of chiral centers to get the maximum number of stereoisomers. There are 2 to the n. So what is the maximum number of possible cholesterol isomers? So let's try to figure that out. So we have 1 here, 1 here, here. That's not 1 right there though, is it? And the reason why this is not 1 right here, because you have a methyl group here and a methyl group, it's the same thing. So there's no stereoisomer. This is not a stereoisomer. So no, none right there. 1, 2. I think that's it. So that means we have 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the 8. Means we have 256 different possible cholesterol isomers. If I counted all my stereoisomers correctly. Anyone find a stereoisomer that I didn't find here? Hopefully I got them all. I got 1, 2, 3, 4, 5, 6, 7, 8. That's not one right there. I think I got them all. So any compound with only one chiral center will be a chiral compound. So with more than one chiral center, a compound may not be chiral. It may have a plane of symmetry. So it says consider the two isomers below which possesses two chiral centers. So the two chiral centers are here and here and here and here. But this one has a plane of symmetry down here because it looks the same on both sides. And the cis isomer has a plane of symmetry, which means it will be superimposable on its mirror image and is not a chiral compound. So that means this is chiral here. Here, this compound is chiral. This is achiral. So it's not a chiral compound. It has a mirror image superimposable on itself. Well, if you divide it, this is what I meant. If you divide it right here, that's that mirror image right there. It looks the same on both sides. Now, if you divide this right here, you know, if we just consider that, I'm going to try my best. We have one up right here. Then we have one down right here. And that's not the same thing on both sides, but here it's the same thing. We have a CH3 up, we have a CH3 up, you know, therefore there has a mirror image. I think this is a good time to stop, so I'm going to go ahead and stop. If you have any questions, just and I just wanted to say I'm still recording, so I enjoyed recording. I'll see you tomorrow.